Greetings everyone, I'm Sankalp Sieghardt and today me and my colleague Richard Anslow will talk about wireless condition-based monitoring development platform from ADI. In this webinar, we'll introduce what condition-based monitoring is along with why there is a need for condition-based monitoring before introducing ADI's solution, that is Voyager 3 wireless condition-based monitoring platform, along with its various use cases and concluding with the ordering information for the platform. We hear this term, CbM or condition-based monitoring, being thrown around a lot. What exactly is condition-based monitoring? CbM or condition-based monitoring is the monitoring of the condition of an asset using data collected by different sensors to estimate machine health, detect anomalous behavior long before any problem becomes an issue. Now that we have an idea about what CbM is, let us understand the need for CbM. The cost of unscheduled downtime can reach up to 23% of the production costs. Condition-based monitoring not only reduces maintenance breakdown, it reduces unplanned failure and downtime and the mean time to repair, thereby reducing maintenance costs. This leads to increase in machine life and increased productivity and profitability. Real-time continuous condition monitoring applications continue to grow in importance as equipment manufacturers look to increase asset utilization with real-time monitoring of equipment to extend equipment lifespans and increase throughput by utilizing predictive maintenance techniques to reduce maintenance costs and asset downtime. Condition monitoring is also deployed to improve manufacturing quality and increase safety in manufacturing plants. Given that unscheduled downtime can amount to nearly a quarter of total manufacturing costs, predictive maintenance has the potential to unlock significant savings and productivity. Growth in new condition monitoring developments will be across a wide range of industries including manufacturing, water and wastewater treatment, food and beverage, pharmaceuticals, metal and mining, paper and pulp, energy, and oil and gas installations. Within these industries, condition monitoring applications are expanding beyond the traditional rotating equipment applications like pump, compressors, and fan to new applications in CNC machine tools, encoders, conveyor belts, robotics, and instruments. Analog Devices offers complete signal chain for condition-based monitoring solutions. From sensing modalities and data acquisition to power management and asset monitoring solutions, Analog Devices helps customers accelerate their CbM development with system-level solutions. Now, I will pass you on to my colleague Richard, who will delve into the technical details of the wireless condition-based monitoring platform.
Thank you, Sankalp. So hi everyone, my name is Richard Anslow. I'm a System Applications Engineer in the Industrial Automation Business Unit in Analog Devices. I will now provide you with an overview of the technical features of the Voyager platform. Condition-based monitoring is truly a system design problem. You cannot design and evaluate hardware and software for vibration monitoring without considering the mechanical enclosure and attachment, as well as gaining insights from the gathered data. Analog Devices' full CbM system design options enable the customer to consider mechanical design and AI insights. Our portfolio includes PCB solutions designed to fit mechanical enclosures, which are available from our partners such as AMC Tech. AI insights are available using ADI's AutoSense technology. All of these benefits are combined with Analog Devices' deep domain expertise in mixed signal, hardware design, and accompanying embedded software. This slide provides an overview of Analog Devices' CbM development platforms and deployable solutions. We provide reference designs, signal chain modules with integrated MEMS and signal conditioning, wired and wireless communication and signal chain platforms, and platforms designed for algorithm development. In addition, we provide deployable solutions in the form of ADI AutoSense AI and PDM, as well as high and low frequency wired house sensors from partners such as AMC Tech. Our presentation today will focus on the wireless platform highlighted in green on the left-hand side of this slide. The Voyager 3 kit is a system evaluation solution for a wireless signal chain for MEMS accelerometer-based vibration monitoring. This kit enables customers to, firstly, rapidly deploy a wireless solution to a machine or test setup. Secondly, to evaluate ADI MEMS sensor technology for vibration monitoring. Thirdly, to evaluate ADI smart mesh technology for industrial wireless sensing. And finally, also to evaluate ADI's low-power 16-bit ADC and ultra-low power MCU devices. The overall aim is to accelerate customer asset monitoring and solution development. This slide gives a high-level overview of the Voyager platform key features. Two key elements are the vibration monitoring mode and the network manager, as illustrated on the right-hand side of the slide. The wireless vibration monitoring mode includes a mechanical enclosure and attachment hardware, including a quarter 28-inch industry standard stud attachment. The Voyager solution can be directly mounted to a motor or test fixture using this stud attachment. The mode also includes a 3-axis 1.5 kHz ADXL356 vibration sensor board, as well as signal conditioning and microcontroller board using the ADUCM 4050 microcontroller. A robust low-power smart mesh LTP5901 board is included with chip antenna. The kit includes a smart mesh USB dongle, which serves as a network manager for the wireless network. We have developed embedded firmware for the wireless mode, as well as a PC-side Python GUI. The PC-side GUI displays network information, as well as acceleration time series and FFT data. There are several useful features included in the GUI, including motor harmonic matching and bearing fault frequency plotting. The Voyager kits stocked in ADI's warehouse are already flashed with embedded firmware, so a customer can get up and running quickly with their system design. JTAG programming and interface boards are provided in the kit for customers who want to do their own embedded development. All of this software is open source and is available on ADI's GitHub landing page. This slide provides some more information on the GUI, which enables evaluation of real industrial equipment. The GUI provides some useful markers for displaying the expected harmonics of an ideal motor, which can be used to compare to the real motor being analyzed. The GUI can also be used to analyze bearing defects. Because of the physics of bearing design, each bearing's defect frequencies can be computed based on the bearing geometries, the speed of rotation, and the defect type. The Voyager GUI includes a useful bearing characteristics window which can be used to input bearing data and display both BPFO and BPFI. The BPFO is a frequency generated when a rolling bearing element passes a defect on the bearing outer ring. The BPFI is the frequency generated when a rolling element passes a defect on the bearing inner ring. The Voyager GUI also includes the capability to perform statistical analysis on the raw data streamed from the wireless mode. Common CbM statistics such as peak-to-peak of the measured vibration data can be computed and displayed. The GUI screenshot shown on the slide shows the raw time series data and the corresponding FFT data. The FFT data plot can be changed to a statistical plot instead by clicking on the drop-down menu. Alarm values can be set on the peak-to-peak vibration measured at the mode. If the mode exceeds a set peak-to-peak threshold, then the mode LED color will change from green to red. This is a useful indicator for a lab setup where a bearing fault is indicated visually on the mode and displayed on the GUI. The GUI and firmware that we provide have been optimized so that a customer can evaluate a real mesh network. The Voyager kit has been tested for smart mesh mode hopping. This is where a mode, which is out of range of the network manager, can hop through an in-range mode. The green arrow shown on this slide indicates a direct connection between the wireless smart mesh mode and the network manager. The orange arrow shows an indirect connection between a wireless mode and the smart mesh manager. As such, one mode hops its data stream through another mode to reach the network manager. The multiple hops network ensures that out-of-range modes can stream data to the network manager. This slide provides an overview of the Voyager hardware implementation. The wireless CbM mode consists of two hardware PCBs. One PCB is used for the ADXL356 triaxial vibration sensor and data acquisition signal chain. The second PCB includes a microcontroller and smart mesh antenna PCB. The Smart Mesh Manager is a standalone USB dongle placed in the PC. This slide provides a more detailed overview of the ADXL356 sensor signal chain. The ADA4807 and discrete low-pass filters, which are not shown, buffer and provide low noise signals to the three interleaved AD7685 16-bit ADCs. The AD7685 ADCs are interleaved to simultaneously sample the triaxial MEMS input signals with the same serial clock input from the MCU board. This results in an optimal sampling bandwidth for the system. Power is delivered from a battery and routed to the MCU and ADXL356 sensor signal chain. A tiny ADP150 regulator is used to provide a low noise 3.3 volts output for the circuit. The TMP36 sensor is also added, as common industrial motor faults such as bearing failure are usually accompanied by a corresponding increase in temperature. Vibration data and temperature data provide multiple fault signatures as such for this system. This slide shows the MCU and Smart Mesh signal chain. The ultra-low power ATUCM 4050 is used to gather data over the SPI bus from the ADXL356 MEMS sensor signal chain, as I already noted. The ADUCM 4050 communicates over UART to the LTP5901 Smart Mesh wireless module. The MCU board also includes a number of regulators used to power all of the MCU components and also to route power to the ADXL356 sensor board. Optional NAND flash storage is available on the MCU PCB. Moving on now, the slide presents some details on the use cases and limitations of using this platform and the existing software setup. So firstly, the wireless mode measures approximately 100mm by 45mm, so it's best suited to larger machines and systems. The focus of the evaluation software that we provide is visualization of raw time domain and FFT data with continuous streaming. As such, the software that we provide does not sample and store data locally on the mote. Because the mote continuously streams data, there is no lower power modes enabled. However, having said all this, if the customer wants to experiment, the hardware provides full capability to be able to experiment and provide low power modes. For example, when the mote takes some vibration data samples and stores that data locally in local memory using the NAND flash as mentioned on the previous slide. As mentioned already, all code is provided open source for the customer to experiment with. Finally, the wireless condition-based monitoring evaluation platform is fully released on the ADI website. The full kit can be ordered using the EV-CbM-Voyager 3-1Z part number and is priced at $350 per kit. You can order the kit and learn more using the links on the right hand side of this slide. That completes today's presentation. Thank you very much for listening, and for more information please see the links on the right hand side of this slide.